Entropy analysis. This topic introduces entropy analysis as an extension of the second law of thermodynamics for evaluating energy systems. The main focus is how imperfections in real processes are measured through entropy generation. Entropy is used as a tool to judge process direction and energy quality. This concept is essential to understand why not all thermal energy can be converted into work. This chapter forms the foundation for analyzing devices such as turbines, compressors, and nozzles. Lesson Plan Thermodynamics 1. This slide shows where entropy analysis fits within the overall structure of Thermodynamics 1. This topic is built upon concepts of energy, the first law, and the second law of thermodynamics. Students are expected to already understand closed systems, control volumes, and energy balances. With this sequence, entropy analysis becomes a logical and deeper continuation. This structure emphasizes that entropy is not a separate topic, but the core of real system analysis. Learning outcome. The learning outcomes emphasize the ability to analyze reversible steady flow work and methods to reduce compressor power. Students are also expected to explain isentropic efficiency for turbines, compressors, and nozzles. The core of this chapter is to derive and apply the general entropy balance relation. From this, entropy generation is used as a measure of process imperfection. With these skills, the quality and efficiency of thermal processes can be evaluated systematically. Reversible work in systems. The concept of reversible work is introduced for both steady flow systems and closed systems. In steady flow systems, work is expressed as the integral of VdP, which depends on the pressure-specific volume relationship. In closed systems, work depends on volume change under varying pressure. Both approaches show that the process path strongly affects the work produced. This becomes the basis for comparing ideal and real processes. Steady flow work insights. Work in steady flow systems is strongly influenced by pressure and specific volume changes. The larger the specific volume of the fluid, the greater the work potential involved in the process. Mathematically, the work is calculated from the integral between inlet and outlet states. This shows that fluid properties are crucial in the design of turbines and compressors. Therefore, the choice of operating conditions strongly determines system performance. Work output depends on specific volume and pressure changes during a process. Reversible versus irreversible turbines. A reversible turbine produces maximum work because there are no losses due to friction or other irreversibilities. Both reversible and irreversible turbines may operate between the same pressure and temperature limits. However, real turbines always suffer work losses due to friction and turbulence. This difference in work is called work loss and is directly related to entropy generation. This concept emphasizes the importance of approaching ideal conditions in machine design. The isentropic compression process is the most efficient because there is no heat transfer and no entropy generation. The polytropic process lies between isentropic and isothermal, depending on the amount of heat transfer. The isothermal process maintains constant temperature but requires maximum heat rejection. The shape of the curves on the PV diagram shows the difference in work requirements for each process. This comparison is important for understanding strategies to reduce compressor work. Two-stage compression, intercooling. Intercooling between two compression stages significantly reduces the total required work. By lowering the temperature before the next stage, the specific volume is also reduced, which decreases the work. The PV and TS diagrams show how the process path becomes closer to isothermal. The resulting process usually follows a more favorable polytropic path. This technique is widely used in industrial compression systems for energy efficiency. Isentropic versus actual processes. An isentropic process is an ideal adiabatic process without irreversibilities and provides maximum performance. Real processes always experience friction, unwanted heat transfer, and other imperfections. As a result, entropy in real processes always increases compared to the ideal case. The difference between these two processes is used to define isentropic efficiency. This concept becomes the basis for evaluating the performance of turbines, compressors, and nozzles. The HS diagram for turbine processes. In an HS diagram, it is used to visualize the difference between isentropic and actual processes in a turbine. In an isentropic process, expansion occurs at constant entropy, resulting in maximum work output. In a real process, irreversibilities cause entropy to increase and work to decrease. The difference between these two paths represents the work loss due to process imperfections. This diagram is very helpful to graphically understand the reduction in turbine performance. Answer: C. The isentropic process maintains constant entropy, maximizing work output, while the actual process involves irreversibilities, leading to higher entropy and lower work output. Explanation: A. The isentropic process results in higher entropy and lower work output compared to the actual process. This is incorrect because the isentropic process maintains constant entropy and maximizes work output, while the actual process has higher entropy and lower work output due to irreversibilities. B. The actual process maintains constant entropy, leading to maximum work output. This is incorrect because the actual process involves irreversibilities that increase entropy and result in lower work output compared to the isentropic process. C. The isentropic process maintains constant entropy, maximizing work output, while the actual process involves irreversibilities, leading to higher entropy and lower work output. This is the correct answer because it accurately describes the ideal behavior of the isentropic process and the impact of irreversibilities in the actual process. D. The actual process results in lower entropy and higher work output compared to the isentropic process. This is incorrect because the actual process has higher entropy and lower work output due to irreversibilities. HS diagram for compressor processes. In a compressor, the isentropic process requires the minimum work because there is no entropy generation. The real process requires more work due to friction and internal irreversibilities. On the HS diagram, the difference between the isentropic and actual paths shows the additional required work. This difference represents the efficiency loss of the compressor. With this diagram, compressor performance can be analyzed both quantitatively and visually. Compressor cooling benefits. Cooling in a compressor reduces the temperature rise during the compression process. With a lower temperature, the specific volume of the fluid is also smaller, which reduces the required work. Cooling water absorbs heat from the compressor to improve overall system efficiency. This process also helps maintain operational stability and prevent thermal damage. Therefore, cooling is an important strategy in compression system design. HS diagram for nozzle processes. In a nozzle, the isentropic process converts enthalpy into kinetic energy with maximum effectiveness, resulting in maximum exit velocity. In the real process, part of the energy is lost due to friction and other irreversibilities. This causes a lower exit velocity and higher entropy. The difference between the two paths on the HS diagram shows this energy loss. This diagram helps in understanding nozzle efficiency conceptually. Nozzle performance comparison. A real nozzle experiences friction, which causes a higher exit temperature and lower velocity. In contrast, an isentropic nozzle produces a lower exit temperature and higher velocity. Heat generated by friction reduces the energy conversion efficiency. The numerical example in the figure shows a significant performance difference. This emphasizes the importance of minimizing friction in nozzle design. Friction causes higher exit temperature and reduced velocity, leading to a decrease in energy conversion efficiency. Energy and entropy balances. The energy balance states that the change in system energy equals energy input minus energy output. The entropy balance adds one important term, which is entropy generation due to irreversibilities. Entropy generation is always zero or positive, never negative. This is a quantitative statement of the second law of thermodynamics. With these two balances, system performance can be analyzed more completely. Heat and entropy transfer. Every heat transfer is always accompanied by entropy transfer, whose magnitude equals Q divided by the boundary temperature. The higher the boundary temperature, the smaller the entropy transferred for the same amount of heat. This entropy transfer occurs at the interface between the system and the surroundings. This concept shows that temperature strongly affects the quality of thermal energy. Therefore, entropy analysis always involves boundary temperature. Entropy and work transfer. Work crossing the system boundary does not carry entropy. However, friction and work dissipation inside the system generate entropy internally. Mechanical energy that is dissipated is converted into a lower quality form of energy. This process always increases the total entropy of the system. This concept explains why lost work cannot be fully recovered. Mass flow and entropy always carries both energy and entropy. This means that every control volume analysis must consider the entropy contribution of mass flow. It is impossible to have mass transfer without simultaneous entropy transfer. Therefore, energy and entropy balances are always linked in flow systems. This concept forms the basis for analyzing turbines, compressors, and heat exchangers. Entropy transfer mechanisms. Entropy can be transferred through two main mechanisms, which are mass flow and heat transfer. In addition, entropy can also be generated inside the system due to irreversibilities. This entropy generation causes the total entropy of the system and surroundings to always increase. Mathematically, the change in system entropy is the result of these three contributions. This principle is the general statement of the second law of thermodynamics for real systems. Answer B. Entropy enters or exits the system with mass flow across the boundaries and increases due to irreversibilities. Explanation. A. Entropy is generated only through heat transfer across the system boundary. This is incorrect because entropy is not only generated through heat transfer, but also due to irreversibilities, even without heat transfer. B. Entropy enters or exits the system with mass flow across the boundaries and increases due to irreversibilities. This is the correct answer because entropy does enter and exit with mass flow, and it always increases due to irreversibilities, as described in the question. C. Entropy generation only occurs when heat is transferred into the system. This is incorrect because entropy generation can occur due to irreversibilities in the system, not just from heat transfer into the system. D. Entropy remains constant as long as there is no heat flow or mass transfer. This is incorrect because entropy can still increase due to irreversibilities, even without heat or mass transfer. Extended entropy balance. In the extended entropy balance, the immediate surroundings that interact with the system are also taken into account. Entropy generation can occur not only inside the system, but also outside the system, for example, in the separating wall. Heat transfer to the surroundings contributes to the total entropy change. By including the surroundings, the analysis becomes more complete and realistic. This approach is important to understand the actual location of entropy generation.
Entropy generation in heat transfer, cases A, B, C. Case A shows heat transfer directly from the system to the surroundings without considering the wall. Case B shows that the wall as a heat transfer medium affects the temperature gradient and entropy generation. In this case, entropy is generated inside the wall due to finite temperature differences. Case C analyzes the temperature distribution in more detail in the system, wall, and surroundings. This step-by-step approach helps to understand where and why entropy is generated.
Entropy changes in control volume. The change of entropy in a control volume comes from three sources, which are heat transfer, mass flow, and internal entropy generation. Heat entering or leaving carries entropy equal to Q divided by the boundary temperature. Mass flow carries entropy according to the specific entropy of the fluid. Inside the system, irreversibilities always generate additional entropy. This balance is used to analyze almost all steady flow devices.
Entropy in steady flow devices. In adiabatic flow, entropy change is caused only by work and internal entropy generation. If the process is reversible, entropy remains constant from inlet to outlet. If irreversibilities are present, entropy always increases along the flow. This applies to turbines, compressors, nozzles, and diffusers. This principle becomes the basis for judging how far a device deviates from ideal conditions.
In adiabatic flow, entropy increases due to irreversibilities with no heat transfer and changes caused by work and internal generation.
References. This slide shows that all figures and most concepts are taken from the book Thermodynamics, an Engineering Approach by Chengel, Bowles, and Kanolu. This book is one of the main references in engineering thermodynamics education. Using this reference ensures that the discussion follows well-established international standards. It also makes it easier for students to study the material in more depth independently. With a clear reference, consistency between the lecture and the textbook can be maintained.